Please go ahead.
Yeah, thank you. Hi everyone, I'm Hatranphd and I'm working on reduced Hatranphd device of a number field under guidance of Professor Renesco. And today I would like to discuss with you about what I'm doing. I will represent in 3 parts. The first part is to review about Hatranphd divisor, Hatranphd class group, and reduced Hatranphd divisor of a number field. And the second part is to show 2 generalization of reduced Hatranphd divisor, which we call C-reduced, and the second is strongly C-reduced Hatranphd divisor, then their properties. And the last part is I want to show one of the application of using C-reduced Hatranphd divisor in computing the function A0 of quadratic field and the number field of unit group of rank 2. But here I only give example for real cubic field. Can you hear?
Trust it.
Okay. And first I want to recall you about Hatranphd divisor of a number field. They are actually analogous to the divisor on the curve, algebraic curve. And if you have an algebraic curve and the divisor have a formal form like that, here np's are integers and p's are the points on the curve. And you make a similar for number field, but you replace the points on the curve by the prime ideal of f. Here is prime ideal of f, and the coefficient and p's are still integers, but we add the second part with sigma here, the infinite prime of f, but the coefficients are in R. Sorry. Then the set of all of Hatranphd divisor of f form a group, and we denote by def. We also define the degree of a divisor with this formula. And I want to show you some analogy between divisor on a curve and Hatranphd divisor of a field, of a number field. You have corresponding to principal Hatranphd divisor, corresponding to principal divisor, you have principal Hatranphd divisor. You have, for a curve, you have p-cat group, then for a number field, you have Hatranphd class group. You have canonical divisor, kappa, then here you have the inverse difference of the number field. And specifically, you have Riemann-Roch theorem about the relation between the dimension of Riemann-Roch space. I denote by H0D here, and the degree of the divisor with G here, the G naught of the curve. Then similarly, we have the Riemann-Roch for number field like this. And we also have H0D, here is the dimension of Riemann-Roch space, similar to the dimension of Riemann-Roch space. And we replace G minus 1 here by a log of half of log delta. Here delta is a discriminant of a number field. And at the end of this talk, I will show you how to compute this function, and so on. The next part I would like to introduce about the Hermitian-like bundle associated to an Hatranphd divisor. Let me recall you about FR. This is defined by the tensor product of f and r over q. Then it's isomorphic to this R algebra. And on this algebra, you have a scalar product defined by the trace map like that. So you can compute, you have the length of the vector used by the trace maps. You have the formula like that with degree of sigma here is 1 in case sigma is real, and in other case it's convex, then the degree is 2. And now you take Hatranphd divisor D with that form, and we denote by I the fractional ideal of f. by compute by this formula and use U is the vector in Fr totally positive. And the pair RU is equal to the Hermitian line bundle associated to D. So the Hermitian line bundle of an Dirac divisor has two parts. The first part is the fractional ideal, and the second part is the vector used in Fr. And the first part we call the finite parts, and the second part is corresponding to the infinite coefficient. We call the infinite part of D. And we can see that there's a bijection between the Dirac divisor and the Hermitian line bundle associated to that divisor. So we can identity two notions from now. So from now, instead of write a long formula like this, I will refer the pair of Hermitian line bundle like this. And the next part is, oh, it doesn't work. Okay. It will recall about the Dirac class group of the number field. We denote by x0f, and this is the analog of the class group on a curve, of an algebraic curve. And first, we say that the set of all Dirac divisors of degree 0, it forms a group, and we denote by x0f. Then we define the principal Dirac divisor as the following. We take a non-zero element f, then we denote bracket f is the principal Dirac divisor with the Hermitian line bundle with the finite parts is the principal ideal generated by f minus 1, and the infinite parts is the vector absolute value of f in Fr like that. And by the product formula, we can see that any principal Dirac divisor has degree 0, so it contains in diff 0f. And we can take the quotient to have x 0f is the quotient of diff 0f by its group of all principal Dirac divisor to have the Dirac class group of the number field. Is it too fast? For you, it's okay. I know how I work with other people.
So far, it's okay.
So far, it's okay.
Okay.
Later on, that you should go slower.
Okay. And I want to show you the structure of x0f. First, we denote by some sigma 0 like that, R0 like it's a vector space of satisfy the condition that you take the sum of the coordinate with coefficient in degree of sigma is 0, and denote by lambda this subset is the lattice. And because any element epsilon here have norm 1, so when we take the log here, it satisfies the condition here. That's why we have lambda is contained in this vector space, and so we can take the quotient. Because lambda is a lattice, so you have T0 is a torus. And because of Dirichlet unit theorem, you have lambda is torus of dimension R1 plus R2 minus 1. R1 is the number of real prime ideal, and R2 is the number of convex prime ideal. So T0 is a convex real torus of that dimensions. And we have the sequence here, see, XX. Here, you take the vector used here to the Dirac divisor from C0 to pick 0f. You take a vector U, become the vector, the Dirac divisor with Hermitian line bundle OF here. And from pick 0 to the class group of F, you take the pair of Hermitian line bundle RU to the class of Brown ideal of the ideal I in class group of F, and we have the exact sequence. That's why you have the corollary at below that if you have two class of divisor on pick 0f at the same connected component, then their difference is the divisor OFU for some unique use up to some multiplication, some uniques.
Can you remind me what is the topology on peak 0?
I will go to it later. Sorry, I want to show the pictures first, so I will go to there later. And so from the exact sequence here, we can see how it looks like. I will try to draw it so you can see how pick 0 look like in real quadratic field and real cubic field. We have, by some calculation, you can see that the volume of T0 it can computed by this formula. Here, n is the degree of the number field, R2 is the number of complex prime ideal of F, and IF is the regulator of F.
It's just the product topology.
Yeah. No, we have the topology on T0, and so that we use it for pick 0f by the relationship at the end. I will show you just after one slide. And we have, so if we know about the volume of T0, we can know the regulator of the number field, because we can know easily the degree of number field and R2. N and R2 is, we can know easily, so we can know the regulator of number field if we know the volume of T0. And moreover, the number, the connected component of pick 0 is the class number. So, in other words, if we know pick 0f, we can know some information of the number field like regulator or class number of the number field. Like for example, in case of real quadratic field, then T0 have dimension 1, so it is a circle. And this is T0, and the circumference of T0 here is square root of 2 multiplied by the regulator of the number field. And the number of the circle or the connected component here is the class number of number field. And for example, in a higher degree of a number field like real cubic field, you have similar picture like T0 in this case have dimension 2, so the real torus here, and the number of the tori here is the class number, and the volume of each torus is merely the regulator of number field scaled by the square root of degree of number field. And now I'll show you the metric on pick 0f. Wait. Okay, first this. Now, I would like to show you the ideal lattice associated to each Hatranphd divisor. If you take this is an Hatranphd divisor with Hermitian Lemon UI, then you know by UI, the subset in FR, because it's in FR, we can use the scalar product on FR for IUs, and it becomes an ideal lattice. And we call it the ideal lattice associated to D. And the important result is that if you have a number field of discriminant delta F, then there's a bijection between the group pick 0F and the set of isometry classes of ideal lattice of the same covolume square root of delta F. So now, instead of working on pick 0F, I can work on the set of ideal lattice. They are isometry and have the same covolume square root of delta F. Should I go on now? Okay. And here is the matrix on pick 0f. First, I take a vector use with all the coordinate positive in FR. And we know by log use the vector, but you take log of all the components of U. Then it's contained in FR, so you can take the length, you can compute the length of vector U with the matrix on FR. And you define U, the length of U pix is the minimum of the vector along U prime. Here you take any U prime so that the log of U prime and log U are the same modulo lambda. I'm sorry. In other words, it's defined by this formula. And so you can define the.
Sorry. Maybe it's a stupid question. So lambda, capital lambda, this is a general definition of an orb. It doesn't depend on a specific Arakelov divisor.
Yes, it only depends on the number field.
Only on
because it's defined by this lambda is log of sigma.
Okay. Yeah.
Sigma so that epsilon are units, but not this. So it only depends on the number field. And so you can imagine like here's OF, the rest point is OF, is the lattice with the rest point here. The vector U here, you take U pix, the vector you put it, you come back to the fundamental domain, and the length of the vector V here is now become the length of vector V ground here. You take the minimum. And this pix, the length pix here is actually a distant function on T0 because any divisor on T0 have a form OFU, the Hermitian lavender is OFU, and you define the length of d pix is the length of vector U, the length pix of the vector U. And because you remember the exact sequence before, we have zeros. This is class group of F. So if you take two different class of divisor on pix 0, the same connected component, like the same torus or the same circle, then they are different is some divisor of FU, which use unique up to the multiplication by the unique of F. And you can define the distance between them is the length of the vector U, and you have the matrix pix 0F.
They are in different components?
We don't define the distance between two different.
So the metric is only defined on the connected component?
Yeah. Yes, you're right. Like the same circle or the same torus. We only define on the same connected component. Yeah.
So in cubic field, for example, you consider each torus and you just define a matrix
on each torus. Yeah. Yeah. And the next part is I would like to introduce you about reduced Arakelov divisor of the number field. The first thing I should say is why we want to work on reduced Arakelov divisor of a number field. That's because it can be used for computing the Arakelov class group, and from the Arakelov class group we can know some information of the number field. But let me say some story about reduced Arakelov divisor first. In 1972, Shanks introduced infrastructure of real quadratic field when he computed the regulator of real quadratic field. And 10 years later, Lenstra also described infrastructure of real quadratic field, but he used the term circle groups. And both Shanks and Lenstra said that this structure can be generalized for arbitrary number field. And it's true because after that, in 1983, Williams and his student defined the infrastructure for complex cubic fields. And then, after that, Bachman and Williams in 1988 described for a whole of the number field with unique group of rank 1. And after that, Bachman is the one describe this structure for arbitrary number field. But the scope is the first one give description in terms of reduced Archimedes divisor and Archimedes class group for arbitrary number field in general case. Let me show you how to define the reduced Archimedes divisor for arbitrary number field. We take a fractional ideal I, then I becomes reduced if 1 is minimal in I. It means that 1 is contained in I, and its coefficient is minimum in FR. Means you don't have any non-zero element with all coefficient is less than 1 strictly. It means because I is fractional ideal of F, so you can imagine in FR by infinite branch sigma here. So any element G here, embedding it becomes the vector sigma F in FR, G sorry, in FR. So minimum means the coefficient of this vector is minimum. And one minimum means you cannot find any non-zero element with all coefficient in FR less than 1 strictly. And here is 2 examples. The first case, I is reduced, it's real quadratic field. Then I is the lattice with the rest point here. The first condition is 1 is in I, so the rest point here, 1 is in I. 1 minimum means we'll draw a square of length 1 here, 1 here. Then this square doesn't have any non-zero points of the lattice I inside. And the second case, we have C2 points inside, so it means it's not reduced. And an Archimedes divisor, this equals reduced. If it has a form di is the Archimedes divisor defined by the Hermitian line bundle I and U here. The second component means it has a form U sigma with all coordinates are the same. So these only depend on I. For some I is a fractional ideal which is reduced. And here is some examples. These have a Hermitian line bundle OF1 is 0 divisor here is reduced because 1 is shorted in I, so it's minimal in I. In OF, sorry. The second example is for real quadratic field. I take the real quadratic field with discriminant delta, and any fractional ideal I with this form, and F is computed by this formula with the coefficient ABC in Z with this relation, with this quality and inequality, then I is reduced. So the I is reduced. And here's the small example. The same example like 2, but I take delta, not delta. I think F is the real quadratic field, Q square root of 983. Then I have 8 reduced divisor on T0 lattice. Because the class number is 1, so pick 0 on so T0. And it is symmetric through this line, the vertical line. And you only have 8 reduced divisor. So the number, you can see here we only have finite reduced divisor. And you see it's quite regularly on T0, right? And it's true for any number field because we have the following result. This is the result of Renescope in 2008. The first one said that the set of all reduced Archimedes divisor we denote by red F is finite. That's because if we take any reduced Archimedes divisor D with the form di, then the inverse I minus 1 is integral of non-bounded by this quantity. And we know that the number of integral ideal of non-bounded is finite. And the number of reduced divisor only depend on the fractional ideal, only depend on the ideal I, so it is finite. And the second reason is that if you take any bone of radius log delta x is divided by this formula, then you can find at least one reduced Arachilab divisor D1. It means, for example, you have T0 here, you take a divisor D here, and you take a bone, a circle of radius log delta x here, then there at least one reduced Arachilab divisor here or here. Or in other words, you can say that we have quite many reduced Arachilab divisor.
Yeah.
Sorry?
Can you repeat the last sentence?
Quite many reduced Arachilab divisor.
I didn't
You
get
can count number.
No, I mean, we have,
Many.
I mean, it's quite many, quite.
Oh, quite.
Ah.
Yes. Because any circle of radius log delta x, you can find at least one reduced Arachilab divisor. But the second theorem is that we don't have too much, because in any bone of radius 1, you have at most these reduced Arachilab divisor with any degree of the number field. So from theorem 1 and theorem 2, you can say in like they are distributed quite regularly in pixel array. And this is the reason of scope in 2008. There's one thing is we generalize the definition of reduced Arachilab divisor because some reason as following. The first one is, the reason is when we want to find a reduced Arachilab divisor, we use an algorithm we call reduction algorithm. And this algorithm asks you to find the shortest vector of the lattice associated to that divisor. And you know that finding the shortest vector is a hard problem and consume a lot of time. And moreover, if we only find a reasonable short vector like using MRL algorithm, then it's in polynomial time and it's faster and easier. And we have, here if we have a divisor D from the IU degree 0, and we take L is the lattice associated to D, and we can find an LL reduced basis of L from D1 to Dn. Then the J, the fractional adjunct J divided by this has property that, and we take V is this vector, this is in FR, then it has property that the length of these is bounded by this. Or in other words, these is almost the shortest vector of the lattice. We take V multiplied by L. It's almost the shortest vector of that lattice, and scale by this number. Scale by the number 2 to the power of n minus 1 over 2. And we use this property to define C reduced Arachilab divisor field as follows. First, let me tell you we have two generalization of reduced Arachilab divisor. The first one, that's the original one. But with this one, to find a reduced Arachilab divisor, we need to find the shortest vector of the lattice. So we generalize it to C reduced Arachilab divisor. But for this definition, for a general number field, we do not know how to test whether a given fractional ID is C reduced. We only have an algorithm for real quadratic field. For higher degree of number field, we currently don't know how to do it. And that's why we make it a little bit simple by define strongly C reduced Arachilab divisor. It's stronger than because it can strongly C reduced can imply C reduced, and we can test it easily. First, let me define C reduced Arachilab divisor first, and then we go to strongly C reduced later. Let I the fractional ideal of F, and use the vectors in FR. Then any element g in I, we define the length of g with respect to u, is the length of the vector u, g. This is in fr, so you can compute the length in fr. And once a cone primitive in I if one is in I, and it's not divisible by any integers at least 2. So, and then I define C-reduce divisor as follow. Let's see at least one. A fractional ideals I is called C-reduce if the first condition is one is primitive in I, and the second is that some u so that with respect to the matrix, with respect to u, the length of vector 1 is like almost like the smallest, I mean almost the short, the 1 is almost the shortest vector of the letters I, scaled by the number c. For any this, hold for any g is non-zero in I. So if you scale by c, then 1 is the shortest vector of the letters I with respect to u. Then similarly, we call an Hatranphd divisor D is C-reduced if they are from di for some C-reduced I. Like it's the same like when you define for reduced divisor. And now I would like to show you some example. Let I be a fractional ideal of S and 1 is in I. We assume that 1 is in I. If 1 is the shortest vector of I, then I is C-reduced with C equal to 1. And we only take the vector used in definition with respect to 1. And so the zero divisor is C-reduced with C equal to 1. Because 1 is shorter than the rest. The second example is all of reduced divisor where as we defined before are C-reduced with C equal to 0 of n. And we take use the 1 in the definition. And this example we saw before because I just repeat you remember when I say the reason we define C-reduce? I said that if we use an LLL algorithm, LLL reduce basis, and we can find a C-reduce divisor easily by this way. Like you have a D, a divisor degree 0, you find an LLL reduce basis, then you define J by this way, then you have J is C-reduced with C equal to this number. So by using LLL algorithm, you can find a C-reduced divisor with C equal to this number. And then we define strongly C-reduced as follows. The fractional ideal I is C-reduced if it satisfies both conditions. The first is 1 is primitive in I, and the second is 1 is the shortest vector of I scaled by the number c. We don't need use in the definition of C-reduced before. Like we take out u, so it makes the definition simpler. And we know that the length of the vector 1 here in fr, then the length of the vector 1 is 0 of n with any degree of the number q. So this condition means if we, the second condition means we have 0 of n over c no more than g for any g non-zero in I. It means that if we take the circle, for example in quadratic field we take a row of radius square root of n over c, then this circle doesn't have any non-zero points of I. So in this case, 1 is in I, and suppose that 1 is primitive in I, and the second condition is satisfied, so it is strongly C-reduced. And the second condition, this circle contains some non-zero points of I, so it's not strongly C-reduced. And here's also example. If 1 is a shortest vector of I, then I is strongly series with C equal to 1. So we have OF is strongly 1 reduced. And if Ig reduced, then it's also strongly C reduced with C equal to square root of n. And the last one is, we also use LLL algorithm here. Let I a fractional ideal path. We can find an LLL reduced basis, B1 to Bn. Then we define J by this formula. Then we have J is strongly C reduced with C equal to this number. We suppose that one infinity in J, then we have a strongly C reduced by use LLL algorithm. Okay. And now I want to show you, this is one example. You can compare between reduced, C reduced and strongly C reduced in case C equal to square root of n. For real quadratic field, then we have degree of number theory 2. So C equal to square root of 2 here. The first circle is T0 with the rest point are reduced divisor. And the second is strongly C reduced divisor. And the last one is C reduced divisor. You can see that reduced divisor is also strongly C reduced divisor. Strongly reduced divisor are C reduced divisor.
So in the picture, these dots, they don't look exactly in the same point, but that must be...
They should.
Really?
But it might be just an optical...
yeah, but they are the same point.
Right.
Yeah, you have to believe.
The white stuff is a little bit curvy.
Okay. So you have reduced implies strongly C reduced and strongly C reduced implies C reduced in case C equal to square root of 2. And here's a relationship between these definitions. You have C reduced implies strongly C reduced and implies C reduced in case C equal to square root of n, any degree of number field. And in the other hand, C reduced and strongly C reduced imply reduced in case C equal to 1. Moreover, we always have that strongly C reduced implies C reduced for any C. But after that, then we have to multiply by square root of n. It means C reduced is strongly C reduced, strongly C prime reduced. With C prime equal to C multiplied by square root of n. So it's a little bit weaker than strongly C reduced. We call strongly because it's actually stronger than the normal one. And here is some property. This is the property for reduced. Actually, we call you this for reduced. For reduced divisor, then we have the provision so that they are finite. This is, we saw it before. And for C reduced, we have nearly the same result. It said that the set of C reduced Archimedes divisor is finite. And we also have nearly similar result, but here it depends on C. For reduced, we don't have this part. For C reduced, we add C to the n. And the same for strongly C reduced. And so we have the set of C reduced divisor and strongly C reduced divisor are finite.
So you got the same bound for...
Yeah, for C reduced and strongly C reduced. The same result. Yeah, the second...
Strongly C reduced is stronger definition, so you expect a lower bound.
Yeah, but I only can do the things.
It's true that one implies the other.
Yes, strongly C reduced implies C reduced.
So
the second is weaker than, you're right. The first is stronger than the second. And This is the result for reduce we talked before. Like for any circle of radius log delta f, you can find at least one reduced divisor. And for C reduced and strongly C reduced, you have the same result. In case we have two cases. The first case is C at least square root of n, then you have the same result. That's because reduced implies C reduced and strongly C reduced. It's the trivial result. And in the second case is when C is from 1 to a square root of n. And for C reduced, we have the same result, but the radius is a little bit different. We add square root of n here, comparing to reduced result. And for strongly C result, reduced, the radius is this number. It also depends on C. But C in this case is strictly less than 1. In case C is 1, we don't know if it's true or not. We don't know any good result about this. And the last one is we can bound for the number of reduced Archimedes divisor in your ball of radius 1 in pick 0f. This is the it only depends the number of reduced Archimedes divisor in a unit ball is bounded by this number, and it depends on the degree of number field n. For C reduced, we have similar result, but it depends also on C. And for strongly C reduced, it's nearly the same, but here we don't have, the denominator don't have number n here, but nearly the same. And we, here's their properties. And the last part is, I would like to show you the application of using C reduced in computing these functions. This function define, like, now you take a divisor D with the form, the Hermitian-Leibbender RU, then you define this function by this log of this sum. And because I a fractional ideal, so it's infinite, it has infinite elements. So this sum is infinite. So we will compute it by which we only approximate the value of this function with some small error. By taking sum of just the short element here. Short means bounded by some positive number n. And we only compute it in case U is very large, because if U is short, then it's trivial to compute this sum. And if U is very large, then when we compute this sum, it's very easy to miss many of this number, and you can get the smaller value of this function than its real value. And the trick is you will find some C real or strongly C reduced D prime, which is close to D, and use it for computing this function.
For some special C, or C depends on n, or
in my algorithm, I use C is I use error algorithm. So C in case of C reduced, then C equal to 2.
Okay, that number.
This number.
Yes.
With any degree of number field. But for strongly, then you multiply by square root of n, then you have strongly C reduced. And here how we do it. For example, without loss of generality, we can assume that D is on T0 and other is nearly the same. And assume that it's far away from the origin here. D here, it's far from the zero divisor here. This is T0. And we do like repeating of, you just like double, you find some divisor D here, D1 here, you double D, and you use algorithm to reduce it, and then you double again, and you use algorithm to reduce it, and double until you go to some D prime here, C reduce and close to D. And you use this divisor to compute at D. And I will show you why we can use the prime to compute D. That's it, because this prime here is close to D. So they're different in some divisor O, F, S here. S is short because they are close. So F is short. And we showed before that with J in this case is reduced, C reduced, with C equal to n minus 1 over 2, and the degree of the number field. Then J is reduced, so the norm of J is bounded by the number we saw before, C to the n multiplied by delta F. So norm is bounded. So this is small, we can say small. So we can, that's why now we can find the shortest vector of L, not difficult because S is short, this is small, and this is 9 because it's reduced. So you can compute the short vector of this lattice, and then you compute H0 at D. I already say that. And this is one example in real quadratic field. I think the discriminant is quite large number because you cannot compute the regulator or class number of the number field with this big number by some normal software. But you can still compute this function. Now it's T0, and you take this is the you can say original, the zero divisor. You take this very far from here. I take example like the distance here to here is like 10 to the 20, and you find some divisor diagram here, and you use it to compute at D. And by some calculation I can compute. I have result that this is approximate this number with the error less than 10 to the minus 5. And now this is T0 the same, but I cut a segment on T0 from A to B, put it here, and I want to compute H0 on this segment. It is far from the origin. I can compute at any point here. Then first I find some C-reduced divisor, just some, and then I use this to compute that the other point. Like if I have a point here, I want to compute H0 at here. Then I first look for the closest point. Then closest point is the rest point here. And I use this for computing. And I do for other points. Finally, I have the picture of H0. The rest point are C reduced. In case of real quadratic field, then C is square root of 2. And the second example is real cubic field. I take the F is the real cubic field with a Q alpha, with alpha is the root of the following polynomial, and the discriminant of F is less than 10 to the power 28. It's quite large, and you cannot find the regulator or.
This is more or less random, right?
Yes, random. Yeah, I can take any number. I just try to make it big. Or you can try to show you that it's big. And I cut this is T0, and assume that it's far away from the origin, like 10 to the power 10. Maybe I can do more than, but I take this as an example because the picture looks nice. You cut a rectangle here. Let's say A, B, C, E, far away from the origins, and I want to compute 8 on the point on this rectangle. So first I find some C-reduced divisor, and in case C real quadratic field, then you have C equal to 2, and I have only some C-reduced divisor here. And now for any point, for example D here, I want to compute H0 at D. I look for the closest red point, so this is the closest. And I use this point to compute at D. And I do that for other points, and I get the picture like this. This actually work. I can compute for any number field with unique group of rank 2, because with rank 2 you can plot it. For higher rank you cannot see the picture like this.
How long does it take you to compute such a picture?
For computing it's very fast. I think it's just some 1 or 2 minutes, very fast. And I use Paris GP to compute it, but I had to use Mathematica to plot it. Because Paris GP only plot 2-dimensional objects, so it cannot work with this. But Paris GP can work with real quadratic field. It can plot immediately in 1 second. Just enter and you have immediately result. And these are the references. The main references you cannot see here of UNESCO in 2008, but you cannot see here because it's very short. And thank you for listening. Really tired of listening.
Thank you. Are there
Do you have any questions for me?
any questions? Or remarks? Or?
So what is it coming next? So what's the next?
You mean my plan for this thing?
Yeah, I mean, we saw 2 examples. That you said they were random. But,
Yeah.
Are you planning to make more computations?
You mean for real quadratic field and complex real quadratic field, I can compute for any number field.
So, but what I find a little peculiar is the fact that since this computation only take a couple of seconds, why
Yes.
didn't you make tables of computation?
I can do it, but I just want to show one example. Sorry. Dũng, he just asked me how my thesis is going. I can do for real quadratic field and the number field of unit of rank 2. And when I try with the Paris GP, it worked until, I think, number large until 10 to about 80. Because after that it's a little bit slowly. Because our algorithm is polynomial in the degree of the number field. So when you raise the degree of number field and the discriminant, then it's slowly a little bit.
So you have these cases of real quadratic field and real cubic fields, right?
Yeah, I just show you 2 examples, but I also have
so because the pick 0 was a product of circles or product of
the union of circle,
yes.
the torus.
Or union of torus.
Yeah.
So these are the only 2 cases in which you have simple topology like that.
In the case of unit of rank 1 now.
Can you say again, sorry?
So, I mean, in these 2 cases of real quadratic field and real cubic field, you have
Yes.
union of genus either 1 or 0, right?
Yeah, yeah.
There are other cases in which you have particularly simple.
Yeah. But it's in case of unit of rank 2,
Yes.
you always have torus. But in other case, I think that I can compute it, but I cannot plot it like this. Because I only plot in 3-dimension space. I can compute it. I think it's similar result, but we cannot show the picture like this.
The topology in more general case? I mean, in the case of quadratic field, you have this union of circles.
You have a torus. You have a matrix on the torus.
Okay, so still, even in general case, you have this similar topology, or for field of higher degree.
The torus is it's only depend on the number field. I mean, it's defined by the vector space or some over lambda here, and it only depend on lambda, and you have lambda in the lattice like this, and you can always define the matrix in normal way. We can not imagine how it looks like because the torus in high dimensional, I don't know how it looks like, but you can always define.
You can make a video game and then you can.
But so if you take a biquadratic field.
Biquadratic field.
In which one of the 2 elements is negative and the other is positive, right? So
but that dimension is 1. I mean the torus dimension 1 is the circle, still circle, and I can I computed actually.
Okay.
I didn't show you, but I have it. I have it.
Or in this case?
It's similar like real quadratic field. It's similar because it's only dimension 1.
All right.
But when you represent, it's only different when you represent the ideal I. In the program, you can divide a matrix with dimension 4 by 4. But in real quadratic field, the matrix 2 by 2. In higher dimension, you just n by n. You just make it raised, and you have normal.
Okay.
Yeah.
Very nice.
Thank you.
Any other questions? And then maybe the committee
Has to be.
withdraws in my meets in my office, and I will switch off the camera.